So the proof for the mean value theorem looks like this. And by the way, just a little refresher, the mean value theorem means that the instantaneous rate of change at some point on an interval is going to equal the average rate of change on that closed interval from A to B. That's essentially what it's saying. So here we have instant rate of change, and this is average rate of change. Just to point that out. So the proof for that, we're going to rely on Rolle's theorem to help us prove it. But to start it first, I need to write the equation of the secant line. So essentially, I'm going to write the equation for the line that I'm highlighting right there first. So using the endpoints from A to B, and writing the equation of line, I have to find the slope first. So finding the slope is going to be f of b minus f of a over, so change in y over the change in x, and then writing the equation for the line. I just used one of the 2 points. I used a and f of a, this point right here, highlighting that. But you could have used the other one. It doesn't really matter. We have the slope of the line. Then I did point slope or slope intercept form, not point slope form, not slope intercept form, but point slope form, and then moved the y to the other side. That's why we ended up with a plus f of a on the other side. Then we're going to take that and let g of x be the difference between the function f that we're talking about and this equation of the secant line. So essentially, I'm taking a continuous function that's differentiable and subtracting another continuous function that's differentiable. So I know already that the result, g of x, will end up being differentiable and continuous, but that comes up a little bit later. So I'm defining g of x as being the difference between f of x, the function we were talking about initially, and the line of the secant that I created using the endpoints. So g of x is then equal to f of x minus y. So I just substituted in the equation for the line here, and you just have to be really careful. You got to distribute the negative. So it ends up with a negative down here on the end, down there, right? So by distributing the negative. Once I've done that, then I'm going to evaluate g of x at the endpoints for a and for b. So I'm going to substitute in and find g of a, and I'm going to find g of b. G of a, we're substituting into the equation that I have right here, using an arrow right there. I'm substituting in for a. So like here's my a, and here I substituted in for a in that equation and simplified a little bit. So I get f of a minus, look, a minus a is 0. So essentially, this entire thing becomes just 0. So you end up with f of a minus 0 minus f of a is also just 0. If I have to do the same thing for g of b. So I'm going to substitute in a b. So wherever I saw an x in my g of x function, I'm substituting in a b. And once I substituted in a b, I realized, oh wait, b minus a and b minus a, they actually, when I multiply, they cancel each other out. And that gives me f of b minus, and you got to be really careful here because you have to distribute the negative here. So I put a little set of parentheses around here, which makes it a plus right there. So essentially, we end up with f of b minus f of b plus f of a minus f of a, which is also 0. So now we have g of a and g of b are both equal to 0. That means that g of a is equal to g of b, which is one of the conditions for Rolle's theorem. So for me to apply Rolle's theorem, I need to have the y values at the endpoints equal to each other, and I need to have differentiability and continuity. But since f of x is continuous, it follows that g of x must also be continuous on the closed interval. And if f of x is differentiable, because we're using another differentiable function to do it, we can also assume that g of x is differentiable. So now we have all of the conditions for Rolle's theorem. So by Rolle's theorem, there's a number c on the open interval from a to b such that g of c is equal to 0. So g prime of c is equal to 0. So g prime, if I take the derivative of g of x, which I had up here highlighted in blue. Let's include the f of x. Taking the derivative of the first part of the function is f prime of x. But the second part of the, the y, the derivative of y is actually just it's a line. So it's going to be the slope of the line. So that's why we end up with just the slope of the line as this part right here. So according to Rolle's theorem, I can take that g prime and set equal to 0. So there's some value g prime of c that is equal to 0. So let's follow that logical. That means f prime of c, I'm substituting in a c for every x. So f prime of c is equal to f of b minus f of a over b minus a is equal to 0 using Rolle's theorem. And that means then we can conclude that f prime of c has to equal f of b minus f of a over b minus a. That is what we wanted to conclude based on Rolle's theorem. So we're using Rolle's theorem to help us prove mean value theorem.